Welcome to Under the Microscope, a stage for materials and nanoscience. This podcast is powered by the Science Talk team. Our goal is to provide a stage where scientists can communicate their work and interact with the public. With that in mind, with every episode, we introduce you to a scientist working in the field of materials or nanoscience. In addition to featuring on this podcast, every guest gets the keys to the Real Scientist Nano Twitter account for an entire week. Check it out at realsci_nano. All right, on to today's episode. Hi everyone, my name is Pranoti. I'm your host of Under the Microscope, and today we have with us Amber Lim, who is a PhD researcher at the University of Wisconsin-Madison. And Amber is going to talk to us about crystals, about comics, about calculations, computational work, all of her research. And this is the last episode of season 5 of Under the Microscope. So if you haven't subscribed or followed the podcast already, what the hell are you doing? Go ahead and do that. It is absolutely for free, be it on Spotify, Apple Podcasts, YouTube, Amazon Music, wherever you're listening or watching. Make sure you subscribe, make sure you follow. Let's welcome Amber. Hi, Amber. Lovely to have you here. How are you?
I'm doing great. Thank you, Pranoti. I'm so happy to be here, and I'm really honored that you invited me on here.
Oh, we're very happy to have you. And your research sounds super interesting, so I want to know everything about it. But could you, as a starter, could you explain your research to us in super simple words? Because crystals, comics, calculations, chemistry, it can mean a lot of things. So what, tell us everything.
Yeah, so I am a computational chemist, and I do a lot of calculations on these crystal structures. And so these calculations are really to find out things about the properties, like where are the electrons in the crystals, and what makes this crystal form versus another crystal structure that could possibly form. So specifically, I study intermetallic crystals, and these are super interesting because these crystals are made solely of metal elements. And what's really cool about metals is that they're so diverse. Like more than half the periodic table is made of metal elements. And so these metals can have a lot of different electronics, a lot of different sizes, and a lot of different ways that they react with each other. And because we have such a diversity of metals, these intermetallic crystals, when you mix them together, they can have really, really complicated structures. So my research is to understand why these different complex structures form, what are the principles behind it, and once we understand those principles, we can start thinking about theories to create more interesting structures, and perhaps structures that have properties that other people might use in the future.
Okay. So, okay. So what size are we talking about here when you say metal crystal structure? What size are we talking about to begin with?
Oh yeah, when we talk about crystal structures, we're talking about like all the way down to the atomic scale. So things that are even less than nanometers, we're talking about length scales of angstroms.
Oh, okay. So atom size, so literally atoms at the edges, or the corners rather, not edges, at the corners of the crystal structures. Okay.
Mm-hmm.
Okay. And I remember from my material science and metallurgy days, there are different types of crystal structures. So there is the BCC, HCP, cylindrical, and all of that. So which crystal structure are these the same ones that you're referring to, and which ones do you have like an expertise, like you are the BCC go-to expert or something like that?
Oh yeah, so yes, definitely in the field of intermetallics, we see a lot of those crystal structures that you are familiar with from your introductory like material science or solid state courses. So BCC, FCC. I specifically focus on main group and transition metal intermetallic. So you see that D block straight in the middle, and then those kind of metals and metalloids at the bottom of the P block in the periodic table. So that's my focus personally. But there's other research going on with my coworkers where they talk about like rare earths and all sorts of other crazy metallic compounds.
Okay, so all kinds of different crystal structures with all different combinations with the metals in the D block and the at the bottom of the P block. Which are the metals again? Remind us in the D block, which metals are sitting in the D block, because I don't have a periodic table with me.
Well, luckily for you, I have a periodic table right in front of me. So the D block, so things like iron or even gold and silver, you have some ones that maybe you haven't heard of before, maybe like hafnium or osmium. And specifically some metals that I've personally worked with are scandium and iridium. And then for metals in the E block, I've worked with aluminum, gallium, indium, and tin for me personally, yes.
And then the structures that you work on, these are not like pure gold or pure silver. These are like combinations. So give me some examples of the different kinds of, not elements, what is it called? Not molecules, alloys. What would you
Alloys, yes.
Alloys, right?
Yeah, so we call them, they could be alloys if they're like a mixture of metals and not necessarily have a specific like place in what we call a unit cell, which is like a 3D wallpaper of atoms. It's a repeating unit. So alloys don't necessarily have a like fixed position in that unit cell. We call our structures intermetallics, and specifically intermetallic crystals, because they have fixed places where those atoms are going to be. So things that I've worked on scandium aluminum 3, and actually a couple of the rare earths, so dysprosium aluminum 3, and then also one of my projects, which I'll probably talk about later, I've worked on iridium indium 3.
Okay. And now I have so many questions for you. After this one, I promise I will stop unless I have a question based on your answer. So you mentioned you work with the transition metals, right? Why transition metals? Why don't you work with, I don't know, graphene or carbon or hydrogen? I mean, you're doing computational work, right? So for you, it should not be a problem to. It should be relatively easy to also work with helium, like gases. Or so why do you work with only the D block? Why do you not want to work with the C block and the A block and the other blocks?
That's a very interesting question. In our group, we actually we want to avoid any sort of elements that are organic. And this is because metal bonding in these kind of structures is just so complex. There's a 3 types of bondings, like the Van Arkel's triangle. You may have heard of it. So it's where electrons can be shared in covalent bonds, or they can be transferred in ionic bonds. But then there's also delocalization, where the electrons are kind of like everywhere in the system, and that's metallic bonding. And intermetallics are very interesting because like there's all sorts of these 3 types of bonds between those atoms, and it makes it really complex to understand what's going on in the system. And so we try to avoid the organic compounds because they tend to have mostly like covalent bonding, things that we can like expect, but we're interested in things that we don't know about and we have yet to understand.
Okay, so metallic bonds, that is your kind of area of one of the areas of expertise. Okay, metallic bonds. Okay. That is super interesting because I've worked with graphene and carbon nanotubes and all of that jazz. And there we have the van der Waals forces.
Yes.
The approach is completely like different. And of course, between the carbon atoms, it is the covalent bond. That's really interesting. I never thought about it, but that is super interesting. And as promised, I'm going to stop asking my questions regarding your research, your current research right now. So tell me, how did this happen? So I'm pretty sure a 4 or 5 year old Amber was probably not even aware that there is something called as metallic bonds that she can do in PhD.
Oh, yeah.
So how did this happen? How did you end up being a PhD researcher now at the University of Wisconsin-Madison? Tell me.
Right. So I kind of had a little bit of a roundabout past. So I originally wanted to be a high school chemistry teacher. And in fact, I've taught high school kind of as part of my minor when I was doing my undergraduate studies. But then I remembered that I had done some research actually in high school. And this was part of the Welch program. It's like a Texas program because I'm from Texas. And they send high schoolers into university labs to do like a research program. And so I was at UT Austin under the mentorship of Professor Lauren Webb and Dr. Annette Raigoza. And that was my first taste of academic research. And I was in the lab, like trying to bind these peptides to a surface in like one-step reaction. And I didn't exactly know what was going on, but it was like very interesting. So I was like, let me try this again in college. And so there I went to, that's where I started my work in intermetallics. I was working in Professor Jacoa Bergach's lab with Anton Olinek, Arya, Mansouri Tarani, and now both of those mentors are professors. And I was synthesizing crystals, so taking metal powders and then mixing them together and then arc melting them, which is kind of like shooting a beam of lightning at those metal powders just to like instantly melt them together. And or I could do flux synthesis where I take these metals and them at so that some of those metals are actually liquefied, and then you slowly cool it down so those crystals have a chance to grow. Doing synthesis was really fun, but I did have my samples blow up a couple of times. So Jacoa, who was the PI, he was like, hey, why don't you try some computations? And turns out I really like doing computations. I like working with computers. And from then since, I've only been a computational chemist and like sat down, ran computations, and look at my coworkers' pretty crystals and compliment them on it.
Okay. That is quite interesting. So those outreach programs to get high school students or graduate students into the labs, they actually do pay off. At least in your case, it did pay off. And also finding your way, because this is a question I always like. I'm always wondering, because I used to be an experimental material or nanoscientist. So for me, it's sitting in front of the computer. It's not for me. I can't imagine doing that. I need to go in the lab. I need to produce samples. I need to do the measurements, like tweaking and all of that. But it's good to know you already answered my question about you tried and there were some incidences. Let's call them that, not explosions. Haters will call them explosions. But that's quite interesting. So do you miss the times when the samples actually did not explode in the lab? Do you miss that part?
I do. So I do miss like result in getting the pretty crystals. Like I still like I have those photos saved of like my crystals. Like I have like my phone camera up on the trying to take these really nice pictures. But then I also look back and I did not like programming the furnace. I did not like, spending many minutes like weighing out the powders. And so even though I have some nostalgic memories about doing experiments, and maybe one day I would love to go back and do some experiments, I still think my heart is more with computational chemistry.
Okay, is that what you are telling me, or is this something that you're telling yourself, that let's not explode any more samples? Let's just be happy with. I'm kidding. I'm kidding, of course. That's interesting. That's fascinating. Yeah, it's also fun, right? Because you do the computation, you are predicting the future, so to say.
Yeah.
Or predicting a version of the future, let's put it that way. And then your colleagues or your collaborators are going and doing the actual work of tweaking.
They're realizing my dream.
Exactly. They're realizing your dream, and you still get to take a picture of that dream through the microscope lens with your phone. So it works. It goes hand in hand. That is great. That is.
Hey there, podcast listeners. Are you looking for a fresh podcast that dives into the realms of scientific wonders, shares unique career advice, and where you can learn about the stories of guests who made real scientific discoveries possible?
Then join us at Keep It Science as we aim to unravel mysteries, spark inspiration, and much more. We're all about bringing science closer to you.
We are your co-hosts, Dr. Elizabeth Kugler and
Dr. Ned Gaunt. So keep questioning, keep exploring, and most importantly, keep it science. Make sure to follow us on YouTube, LinkedIn, and X, or wherever you're listening to this from.
bye! Science.
What is it? Who does it?
Why does it matter?
The Science Night podcast answers these questions by giving scientists a place to tell their story.
We also highlight science news and discoveries that will have you asking, "My God, what have I done?"
What weird thing are we going to talk about this week that involves a frog?
They made an organic robot? Didn't they see The Matrix?
Join us every other Friday, wherever you get podcasts, and at scinite.com.
Hi, fancy folks. Welcome to Lux Sci, where we make science fun, approachable, and most of all, fancy. I'm Dr. Lex, former microbiologist, current global health consultant, and enthusiast of all the finer things in life. I'm often joined here by my husband, electrical engineer, inventor, and our audio engineer, Dr. Demos. In this podcast, we take listeners on a journey into the microscopic worlds of luxury items and unravel the fascinating intersection of science and opulence. From how bubbles form in champagne, to the molecular forces that harden clay in a kiln, to the amount of thrust needed to send a rocket to space. No luxurious topic is safe from our insatiable curiosity. We're on a mission to demystify science and show how it drives the world around us. No PhD or lab coat required. So if you've ever wondered how science and luxury seamlessly intertwine, join us as we uncover untold stories, hidden marvels, and the inner workings of scientific discovery and sophistication. Along the way, we'll also chat with amazing scientists and artisans, so subscribe now and let the exploration begin.
That is great. Okay, so because this is something that I also always wonder, because again, I used to be an experimental scientist, so for me it's always fascinating to know if you have a research project that you're super proud of. It can also be one of those exploding ones. It's maybe fun, I don't know. Or sorry, those incidences. Sorry.
Yes.
But do you have a research project that is super close to your heart, or something that you're super proud of, or fun, or a quirky one for whatever reasons? And I know this is a difficult question, right? So could you pick that one research project that you're proud of and explain it to us in the section we call In Other Words?
Yeah, so one of my research projects, so this is actually the last paper I published. So this is a completely theoretical, and but one thing I'm proud of it is that through these calculations, able to predict something that was very close to experiment, which is not always something that happens. Like, a lot of theorists, you can predict anything, you can calculate anything, but does it actually reflect the real world is another question. So this project was about the polymorphs of iridium indium-3. So that's one iridium atom and then three indium atoms. And so there are two polymorphs, which means there's two different like crystal structures it could form in. And this kind of crystal structure could form in another one. And it turns out that these two structures are dependent on temperature. So you have a high temperature crystal structure and a low temperature one. And what was really interesting is that the high temperature crystal structure had a lot of these like empty spaces in the arrangement of the atoms. And turns out these empty spaces are really important because it allows some of these atoms to vibrate into those empty spaces. And so vibration adds a degree of entropy, or kind of like this freedom of movement. And entropy is tied to temperature. So like this was very interesting. And we used one of our methods, which was the DFT chemical pressure method, which is a little bit complex, but this was a relatively inexpensive calculation. And then so this was hinting at, all right, there may be vibrations here, so let's actually confirm it. So I did some more calculations, and indeed, like the lowest energy vibrations corresponded to that motion of those atoms going into those void spaces. So those void spaces were really important. And then so using calculations with what we call those phonon calculations, we were able to predict that phase transition temperature between the low temperature phase and the high temperature phase was about 400 degrees, which is really close to the experimental value of 350 degrees Celsius. And like that may not sound too close, but like you have to remember these are metals, and these phase transition temperatures can happen at thousands of degrees Celsius. So that was really close. And this was like the most basic of calculations. And so being able to do something that was like really fundamental and predict something that was grounded in experimental work was really amazing for me.
This is the dream, right? You have whatever you predict, theoretically what you expect to happen, and then it actually happens when you do the experiment. It's just that is the dream. If only all the theories were proven or confirmed through experiments, the scientist world will be happier. I think the scientific community would be so much happier if that was happening. But that is really cool. Please tell me this paper is published.
It is published. It came out this year.
Excellent. Congratulations. And you're going to talk about this project, this paper and this project when you're taking over the Real Scientist Nano Twitter account.
Of
right?
course. Yes.
Okay. Excellent. Excellent. So, Amber, it's clear to me, it's very, very clear to me that you love the research aspect of being a scientist. And your research, by research, what you mean is completely different than what I mean as an experimental scientist. But it's clear that the research aspect of being a scientist is really, really exciting for you. But in addition to that, there are different aspects of being a scientist, right? So what else do you like about being a scientist?
Honestly, I think my favorite part about being a scientist is just all the people I get to meet and work with. Like you know, it's a very, very big stereotype that scientists are like cold, logical people, but that could not be further away from the truth. You'll find that scientists are so diverse, like not only in just like their background and where they come from, but like a lot of scientists are actually really, really creative. For example, in our department, we have a group of people who created this zine, and the purpose of the zine is just to showcase all the creative things that people do in the department. So people will submit their poetry or their art, or even things that they've like knitted or crocheted. Personally, like I like to draw comics and I like to paint, and so I've submitted that. Outside of that, I mean, you see like people who like they do pottery in their spare time, or they like to go stargazing, or like me, I like to play D&D with a bunch of scientists. And so you have nerds on all sorts of different levels, and people who are just creative, and they're just super compassionate people. So the best part about being a scientist for me is just seeing all the other people who love science but are also their own person.
Right, right. Yeah, scientists are humans at the end of the day, and they are not, they are super fun. Some of the most fun people I know are scientists. And it might be because of the bias, because I used to be a scientist, but it is actually true that scientists are a lot of fun. And it's just, they're more than the lab coats they wear and the safety goggles they have to wear and the gloves. They're so much more than that. And they're normal people. They go stargazing, they play D&D, and they make comics. Tell me
Yes.
more about the comics, young lady. What kind of comics are we talking about here? Like anime, DuckTales, like what?
So personally, like I love anime. I've been into it for like since childhood. So I like to draw like anime comics, and that I keep a little bit separate from my like professional presence, but that's like a hobby I like to do. But using those skills, like I've been thinking about like, hey, what is a good way to communicate my science? So I actually have written a couple of like science related comics which are available on my group's website or Twitter. You can take a look at that. I'll definitely link it when I take over to Twitter. It's been really fun because, like, when comics are very visual, and I think most people are also very visual, and it's really an interesting problem to tackle. Like, how do you break down such a complex topic into a way where people can read it and get a general idea of what's going on, especially for like PhD work or research that is like on the cutting edge and still coming out. So it's been really fun to like draw comics and think of like, oh, what kind of comic should I draw next, so that people can learn about my science and science in general.
Okay. I cannot wait to take a look at your comics and learning, like even the science communication. I thought that you do it for as a hobby, as like a fun thing. I did not know you use comics as a as a channel for science communication as well. That is really, 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 really cool. So, Amber, it sounds to me, I mean, your current workplace also sounds super amazing with showcasing the different sides of the scientists as well. But the research experience in general can always be improved, right? So if you have 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay? Don't.
Oh, I wish you could. But anyways, so one thing, especially since I am a computational chemist, a lot of things I learned was self-taught. So I wish I could just reverse time and teach myself more computer science, because especially a lot of like science nowadays is kind of turning towards more data focused things, and you have like machine learning, you have just gigabytes of data and computations that people are doing. So I wish I had, learned a little bit more computer science, learned about software architecture, and also really learned about like documentation and like, oh man, there are so many times where I have lost track of data or lost track of my code. Like, what was I doing last week? And I just wish I had documented it. So like really learning these kind of basic skills, like it seems like a given skill that anyone could like quickly pick up, but there are actually some best practices to doing these things. And I wish I had learned that a lot earlier, so I wouldn't be, losing so much time and so much like brain power. Mm-hmm. My second wish is that I had wished that I sought out mentors outside of my research group early on, because when you are doing your PhD, you tend to focus on your own research. You hole up in your office, you don't talk to as many people, but it's really good to get an outside perspective and especially get like mentorship from other leaders in your department or even outside of your department. And that would have made my graduate school experience a lot easier. But it's never too late. So yes. And my last wish is not really for me, but it's just kind of for research in general. Research is pretty difficult, so it takes a lot of time and a lot of money. and a lot of people. So funding for research as it stands right now isn't really catching up to like inflation. And so it's really hard to conduct good research if you're worried about like, are you going to get funding? Is the department able to pay those people who are supporting your research fairly? And like, if you don't have funding as a PhD student, you oftentimes have to TA or like teach chemistry, and that cuts away from the time that you're doing research. So if we want to continue to be like on the pioneering edge of science, we really need our governments, industry to really invest in what's going on. So even if there's no immediate benefits now, fundamental research or just research in general can pay off into advancements like 5, 10, or 30 years down the line.
Mm-hmm. Yeah, absolutely. All really valid wishes, I have to say. And I wish I could also turn back time and learn so many skills, so many of these things that no one talks about. How to keep track of your data, how to keep track of your files, how to keep track of like the documentation, the data hygiene, and all. So I think it's very, very important. And the second one was seeking out mentors outside the outside your niche field. I think that's also very important, and that has helped me also immensely. But also, I did not know that so it just happened, and then I'm like, oh, actually, this is cool. So definitely. And the third one as well. It's difficult to be a researcher, and when scientists are asking for money, it's not for themselves, it's for the research. And also the fundamental research is often like, oh, what is its application? But you need fundamental research so that you can have a faster computer in 5 years. That is where it starts. So you know about the Intel chips now, but scientists have been working on them since decades. So this is something very, very important. But yeah, I hope all three of your wishes do come true in some form or the other. I mean, the turning back time might not happen, but maybe you can get tools that can make up for the time that was spent. And now that you know, seeking out mentors, you can always do that. You can continue to do that as well. And the third one, I think when we have scientists like you who are aware of these issues, so to say, that can be things that can be improved, I think the future of science is in good hands. Also fundamental science, fundamental research. So this is absolutely bang on. And I wish I had that magic wand to grant all three of your wishes, but hey, we will make them happen. We are scientists. We make things happen. We don't believe in magic just happening. So Amber, this has been wonderful to get to know you, get to know your research. But before I let you go and do some more computation and or create comics or with crystals and calculations, chemistry and all of that, we mentioned several times Real Scientist Nano Twitter account, and that is the second part of this project. So in addition to being a guest on our Under the Microscope podcast, you also get the keys to the Real Scientist Nano Twitter account for a week. So in that week, what can our followers expect? The more than 3,000 followers that we have.
No pressure, no pressure. I talk to 3,000 people on a daily basis.
Exactly.
I will, talk about myself a little bit, about, the research that's going on, especially about crystal structures, since they're kind of different from, normal molecular chemistry. I'll talk a lot about the fundamental stuff, but I'll try to break it down into really simple bits. Especially, I have a couple comics that explain some of these bits, so you'll get to see some of that. And then also, one of my friends will be defending for her PhD soon. So also talk a little bit about the grad school experience, the things that I wish I knew coming in, and things that I learned throughout my whole time here.
Okay. So we joined the PhD ceremony as well.
Yes.
Do you also do the PhD hat? This is a tradition, at least in Germany. Like the group mates or the colleagues, they make like a fun little sort of a PhD hat, and you get it like based on their experiences with the colleague, where based on like if they like skating, then there would be tiny skateboards or something. So I was working with graphene, so for me they made like a polymer sort of a thick polymer sheet that could hold the hat. And I used to bike a lot. I used to bike to work every day, so they put a bike helmet, and then on top they put the hexagonal sheet, and then they put it, they layered it with gold. I mean, golden plate, not real gold. Then I just added like fun pictures, bits and pieces here and there. So that's usually the tradition. Do you have any such traditions?
I know people do that for undergrad, but I have never heard of it for the PhD. But that's such a cool idea.
I know. You should defend your PhD in Germany. I'm telling you.
You know, I'm just going to move there in the next like 2 months.
Yeah, absolutely. You know, this sounds good. And I'm also looking forward to not just participating or celebrating the PhD, the new doctor on the block, but also the crystals, your work, and your comics as well, and everything else. And we want pictures also, okay? We want the pictures of the Christmas tree or the winter party celebrations. We want everything, okay?
I got you.
Awesome. Excellent. Then thank you very much, Amber. Cannot wait to have you on Real Scientist Nano. Thank you for taking the time speaking with me, and we look forward to keeping in touch as well.
All right. Thank you so much. It was my pleasure.
Thank you for listening to yet another episode of Under the Microscope. If you like this particular episode that you just listened to, feel free to check out our other more than 200 episodes with amazing scientists from all around the world, materials and nanoscientists, and do let us know what kind of science, what kind of material science you would like to hear more about, and we will try to get you a guest accordingly. Thank you for listening yet again. Really appreciate your support. And hey, do consider joining our mailing list. The details are in the episode description. Thank you. See you in the next episode. Bye.